Hello, good evening, learners. Right, I hope had a good exam and everything. Right. Okay. So yeah, we'll start probably from where we had dropped in the last part. So in the last session, we were talking about the guide algorithm in a decision tree, right? And we discussed that how you can use the chi-square formula into finding out the significant variables in a decision tree. So that was where we stopped. So again, in terms of what we are going to cover in today's class, right, there's several agenda which I have with you. One of the agenda is obviously to take the decision tree forward, because again, decision tree in terms of the mathematical part and the explainability, I'll probably focus on that particular issue. That is one thing to look into. The other is the Python implementation of a decision tree algorithm. That's also second agenda that we have in mind. But I know for sure that today we'll not be able to complete both the implementation part as well as the theoretical part. So again, if we talk about the theory, it's more about some mathematics, which we are going to talk today, right? I was looking into the feedback from the last session, and what I understood is that some of the people, they were actually having some difficulty in understanding the maths part. Fair enough. Many of you probably have been in touch of academics for pretty long. But again, what we are doing out here are basic mathematics, right? So yeah. So I think Samip has a question: entropy, Gini impurity. Sure, Samip, we'll take it up. We'll take it up. We'll take it up today. Not to worry. We'll take it up. Right? Okay. I think there someone raised his hand. Probably. No. Thought someone raised his hand. Anyway, let's get ahead. But again, in the meantime, if you have some specific question, for example, Samip had some specific question he had posted. If you have some other questions which is relevant to the parts which we have already covered, please feel free to post that, right? Let me clarify your doubts and then we can probably move ahead. Yeah, any doubts, any question with regard to what we have covered till now, please put it up, right? Otherwise, I'll probably assume that you are good with whatever we have covered, and then I'll get along. As I said that in today's class also, a considerable part we will spend with the mathematics part of the decision tree. See, when we talk about this whole field of ML, I am repeating myself. So there are 4 significant components to it. One of the components is definitely understanding of the business, what the business is talking about, and the business problem to solve. Now, decision tree being a being a supervised learning algorithm. So supervised learning algorithm means basically it's having a target variable, and our focus of interest, that particular target variable only, right? So in the target variable part, in the target variable aspect, so either we are going to predict some particular class or maybe predict some particular numbers. So either it's a classification problem or regression problem. So irrespective of what kind of a problem comes to you, if it's some kind of a supervised learning algorithm, decision tree is one of the many algorithms that we can apply out here. Doesn't matter what exactly is the business domain, as long as there is a target variable of interest, we should apply algorithms like a decision tree or KNN to it, right? Now, the other part is for each of these, so that's the business part. The other is the data part. So obviously, depending on the data which has been presented to you, so obviously you need to have some kind of understanding of the data, in the sense that maybe the business will tell you that what exactly this particular data means. Typically, in the process, what we do in these live sessions are we take some examples where everyone, irrespective of whatever background you're having, you're able to identify that business problem and the data, right? That's the kind of business problem generally we try to solve. But again, I'll encourage you to come up with your own problems. I'm sure that many of you are probably in some kind of a machine learning projects or data science projects in your organization, right? So what we'll do is after the break that we are having, generally at around 60% of the completion of this live sessions, we take a break. So post the break, what we'll do is we'll probably have a discussion as to some of the interesting problems that probably you are confronted with in your organizations, and probably try to discuss that how you can go ahead solving those problems, and whether the algorithms that we have learned out there, whether it will find its use or not. If yes, how? If not, why not? Right? I think that will be a good discussion that we can all have. So please come forward with the problems that you're having. Right? Okay. So let me move ahead. In the meantime, anyone, any other question with regard to whatever we have done in the last class? Apart from a question which Samip had raised, and I had promised Samip that eventually in the course of what we are going to cover, his doubts will get cleared. But yeah, any other questions? Anyone? No? Good. Then let's proceed. 7:08 in my clock, and I see about 14 attendees are there. We are good to go. Again, coming back to the logic of the decision tree, right? So decision tree. The name only says that there is some kind of a decision which goes on, and the tree part, it helps divide the decision into smaller and smaller subparts. So when it comes to the principle of decision tree, we apply the divide and conquer principle. What we try to divide is the data set. How we try to divide? Data set divided on some particular feature, whereby the kind of target variables which are there, we are able to find a solution or a situation where there is not too much disparity in the target variable. Right? Now, how does it mean? And why I'm focusing or stressing on this divide and conquer? Right? Trivial examples from life. Right? Before every voting process, you find that again the different parties which are there, they'll probably try to speak to the MPs, MLAs, and probably find people who are pro for that particular party, right? And try to conquer them. In their division, they are probably not mixing people who are like pro to them and anti to them, right? They are probably trying to divide the groups into such a way that in those groups, they are having more and more people who are homogeneous, right? Because it helps in taking the decision, right? Come to the case of the US election, which happened where Donald Trump had won. In that particular election, one actually thought that Trump will win, right? So at that point in time, what was done was that Donald Trump, he looked into all the data of the people who are there. He looked into the pockets where people are definitely not going to vote him. So what he did was he first focused on the pockets which were probably on the on the middle part, right? They are sitting on the fence or on the wall, and tried to convert them their side using issues like which appeal to those people, right? And then for people who are very much anti against him, he used some separate strategy, right? So like that, the divide and conquer mechanism works. For the decision tree, what we do is that let's talk about the classification problem. The classification problem, we have different categories. And now in the process, if we divide the data randomly, then probably they come with pockets where both the target variables, both the kinds of target variables, depending on the number of classes that you have in the target variable. Let me talk about binary classes, where there are two classes, right? One is if you do randomly, there'll be both types, let's say yes, no, true, false kind of target into those pockets. But otherwise, if you're able to get some particular feature, some particular variable based on which you can do a division, and it very clearly segregates between the classes that you're having, probably will be helpful for you, right? And that's exactly what we try to do, this decision tree. We try to find that particular variable which is very much influencing in terms of dividing the data into homogeneous class. Because again, if the data is divided into heterogeneous class, we probably can't take a decision from that. Only when the division is homogeneous, that's when probably we can take some kind of decision from it. Again, I'll quickly take you to the problem that we did, right? Again, this is the basic process of building and growing decision tree. Select the root node. So root node is where every data point is having, right? And then you test for the root node, right? In terms of whatever features are there. On the basis of which feature can I divide so that the resulting class which I'll get is probably more or less homogeneous, right? And I try to repeat this to a point when I don't have any kind of a heterogeneity in my data, right? So this was the chi-square or algorithm, the chi algorithm, and this was the formula which I talked about, right? The observed value minus the expected value squared divided by the expected value, right? So we find out the chi-square value, and as we have seen that if the observed and the expected value, they are in sync, right? Whatever the observed is saying, the expected also saying the same thing, which means that particular picture doesn't have much bearing on the same, right? But again, find that the observed value is something and the expected value is something which is radically different from it, right? Probably there is a chance that this particular variable is important. What we did was we calculated the chi-square value for each and every variable, right? If the variable is having a very small chi-square value, in fact, chi-square values that you get from this particular formula, that you can convert that into some kind of a probability values. There is actually a chi-square table from where you can get the probability values or the p-values against this chi-square values, right? But again, not that particular part. All we discussed was that higher the chi-square value it is, more important is the variable for doing the splitting. Just to show you, so this was the data that we had, 14 data points, play, don't play. Say for example, out here, whenever you have this case of overcast, so for the overcast case, you find that all the cases it is saying play. None of the cases it is saying don't play. See, for the sunny, 2 cases are saying play, 3 cases are saying don't play. For the rainy, 3 cases are saying play, 2 cases are saying don't play. So it is very close together. But for the overcast, my decision is exactly clear. If it's overcast, go out and play, right? That's what talks about. Talk to the temperature part. In the temperature part, see, whenever the temperature is hot, play, don't play. There are equal cases. I don't know what decision to take, because again, of the 4 data points which I have, who are saying play, who are saying don't play, completely confused, right? But again, come to the part of cool. Cool part, what happens is 3 is saying play, 1 is saying go. So the probability is more towards play. In the previous case where we talked about this outlook, and if the outlook is overcast, you see my decision is completely homogeneous. There are no instances of don't play. All of them they are saying go out and play, right? So if I do a division of my data and somehow this overcast part is there, right? By dividing the data into such a way that there are some cases which move towards the overcast, so I can conquer that particular data point, because again I know for overcast it is always play, right? So similarly we did it for the wind. Here in the wind case, you see that for the wind as strong, 3 and 3, right? Pretty confused. 3 cases are saying play, 3 cases are saying don't play, right? I don't know what decision to take. For the case of weak, it is much better, because of the 8 cases, 6 are saying play. So the decision is tilted more towards the play part. And then for the humidity part, once again, humidity high, difficult to take a decision. Humidity normal, tilted more towards the play part, right? So like that, we will basically split the data, and again, this was what we got from the chi-square values, right? as you can see out here, for the, I'm sorry, not the chi-square value, the p-value which was calculated. So the p-value, you see the temperature is having the maximum p-value, right? Followed by this wind, followed by this outlook, and lastly this humidity. So temperature will be having the maximum influence splitting the data, right? It will ensure that my data is homogeneous once I split with temperature. Last class I showed you the chi-square values, right? Here, same, the chi-square values, they have been converted to the p values, right? Okay, coming to building the decision tree, right? So we selected the feature and split the data into, let's say, binary tree, and then we asked more questions. Right? So see here, I have split, and then I have one blue and one red. So if I have complete blue and complete red, which means I've done a good job. I have done a good job in the sense that there is no confusion, no heterogeneity, right? But again, let's say this blue is not pure blue. There are some reds embedded in it. So I probably need to split it further. So I split it further, right? And once again, we get some reds and some blues. If these reds are completely homogeneous in the sense that there are no blues embedded in those reds, and if the blues, they are completely homogeneous in the sense there are no reds embedded in them, then probably I have reached some kind of a homogeneity. So based on the condition on which I have splitted this particular nodes, right? So this particular node, on the basis of the decision on which I have split it, I'll take them as the important variables, right? Okay, so here also you can see that my red was not a pure red, so I got a chance to divide that into, once again, red and blues, and I'll continue the split until one, if nodes are completely pure, completely homogeneous, only one class remains, right? Either the blue class or the red class, not a intermix of the two. Or the other is a maximum depth is reached, right? So you can also say that in a decision tree, I'll probably build my decision tree up to, let's say, level 2 or level 3, not beyond that. Once the maximum depth is reached, which you have specified, you'll stop, irrespective of the kind of accuracy that you have got, irrespective of the heterogeneity which is there. One question I have the class is that, let's say that I have said that my decision tree will be only up to one level. One level is this one. And as you can understand that if I stop my decision tree at this particular level, there will be a lot of heterogeneity. In that situation, how is that I'm going to take the decision? How is that I'm going to take the decision in that particular situation? Any thoughts? Because I have told explicitly that you stop your decision tree at this particular first level. Don't go beyond that. Right? How am I going to take the decision in this particular case? Let's say that the node had some 100 data point, of which, let's say, 60 has come here and 40 has come here, right? How am I going to take the decision at this particular instant? Yeah, answers? Please participate, right? If you don't question, if you don't challenge yourself, how will you learn, right? Yeah, what do you think? Some answers coming in. So Kavita is saying take the mean or the mode, and Vikas is saying based on a predetermined acceptable impurity level. If 60 is good enough for me, I don't need 100. So again, I'll probably Kavita's answer. So what Kavita is saying is that, see, at this particular point, I have some heterogeneity, right? So let's say in the 60, I have 40 belonging to a class A and 20 belonging to the other class. Same true for this 40. In the 40, I probably have 30 belonging to class B and 10 belonging to class A. In that particular case, I'll probably take the mode, or probably the one which has a maximum mode. This particular case, right? The class where the number is 40, I'll probably take that particular class. In the case for this particular, I'll go with this one because it is the majority. In this particular case, I'll go with this one because this is the majority, right? And that's for a classification problem. In case of a regression problem, as I said, once again, that what we'll do is whatever is the value of all the target variable which we have out here, we'll simply take the average of them. Right? Okay, let's move ahead. And then coming to what probably Vikas was trying to tell us. A performance metric has been achieved. In the sense, when I had fitted the tree up to the first level, what has happened is I needed some kind of a desired performance level. And I've already reached that. Right? If I've already reached that, then I'm good. I'm good. Right? No problem with that. From this small example which is there, can anyone tell me what is the accuracy of this particular tree going to be at the level 1? Accuracy. Accuracy. Remember that we had done all those metric, accuracy, precision, recall. What's the accuracy of this decision tree going to be? Yeah, anyone? Quickly. Kavita is saying low, but again, I need some answer. Saurav is saying 70%. Anand is saying 100%. No, Anand, it's not 100%. Kavita, we need some numbers. Saurav is saying 70. Let's see that is if Saurav's answer is correct or not. So see, there are 100 data points in total. Of this 100 data points, right? This particular one, if my data is amongst this, I'll go for this majority class, which is 40, which means 20 data point I'll probably would have misclassified. Here, there are 40 data point, of which 10 I have misclassified. 30 I have rated correctly. Here, 40 I have rated correctly. 20 has been misclassified. 10 has been misclassified out here. So out of a total 100, 70 data point I have been correctly able to classify properly, right? That's why accuracy is 70%. As Saurav has said, Samrat has given us the same answer. Anand also has given the same answer. Yes, 70% answer. Right? I'll repeat once again. What happened was that whenever my decision nodes they are not completely homogeneous. So in the case of Anand, so Anand probably what you were trying to say was that if it's completely homogeneous in that particular case, yes, my accuracy is 100%. No doubt with that. No doubt with that. Right? But in the case where I have prematurely stopped the tree is prematurely stopped. Right? In that particular case, obviously, I'm going to have some kind of a heterogeneity. And in the heterogeneity part, what will happen is wherever the majority class is there, that will win. Right? So here, I have 60 data points, of which 40 belongs to class A and 20 belongs to class B. Here, I have 40 data points, of which 30 belongs to class B and 10 belongs to class A. Right? So what happens is that when, let's say I'm trying to classify this 10 points, every time I'm saying that this 10 points are of class B because that's the majority, right? So I'll be misclassifying this 10 data points. Similarly here, I'll be misclassifying this 20 data points. So of those 100, the 30 data points will be misclassified had I stopped at this particular level. So that's why the accuracy is 70%. Right? Had I done a complete splitting, complete growth of the tree where it was homogeneous, then probably my accuracy would have been 100%. Okay, so Kavita is having an interesting question. So what will be the precision, right? Precision of, so precision is the positive predictive value, right? So for the positive predictive value, it is, so a positive I'm predicting as 60, of which 40 is correct. So 40 by 60 is the answer. Correct, Kavita? Correct, right? Okay, let's move ahead. I think you got the idea. Okay. In terms of selecting the splitting topology, right? There are so many things which are there. The classification error is there, Gini index, entropy, chi-square, those kind of things are there, and also the variance reduction, right? So those are the techniques which we measure the impurity, and then the selection mechanism is by using things called gain ratio or the information gain. So let's understand that what are those measures of impurity, how it is being done. Okay, so Braj is saying you don't have the permission to post to everyone in the chat box. Fair enough, Braj, right? So I'll keep that in mind. So yeah, whenever something comes up next time, I'll definitely put it up for the sake of the entire. Okay. I'm not able to get this. Okay, now it's getting clear. Okay. See, there's a lot of confusion which I've seen with people with this particular term, which is called impurity. What exactly is this impurity thing? See, let's talk about how you take water, right? So whenever you are taking the water, right? Water is coming from your water filter. You're obviously looking at water which is of pure, right? If that is not happening, then what you will do, you will try to remove the purity from the impurity from the water, right? I'm sure that most of you have this aquaguards in your home, and for this aquaguards, what you do is there are several filters like this iron filter, right? There's TDS filter, all those things are there. And what they're doing exactly at every point or every step, they're trying to ensure that the impurity in the water they're catching hold of, so that finally the water that you consume is pure, right? You've seen, right? In your let's say aquaguard or purity kind of things, there are two taps. One tap will give out the clean water, the other tap will basically get the impure water. So next time, if you get this chance, just test in your home itself. Test the TDS of the water which comes out from the other channel vis-a-vis the TDS of water which comes out from the main channel. Find a lot of difference out there, right? In terms of a pure case, so this is where you have completely pure data point. Why? Because only the green classes exist. No other classes exist out here. That is a totally pure case. Come to the case of this pure part. So here, along with this green, there are some blues and some reds, right? And obviously, since you don't consume water, which is having impurity, so how can you take their decisions where probably there are a lot of ambiguity or impurity? So that's why what we need to do is we need to find out those particular filters for decision also, which can block or catch hold of impurities so that you're able to take better decisions. Right? Fair enough? So let's go ahead. Okay. Coming to the features of impurity. Right? So again, whenever we talk about of a data, if the data, let me once again clarify, if the data is having only one kind of a class, that's a complete pure data, and the impurity value is 0 out there. In this particular case, the impurity value on the left hand side is 0. No impurities. Right? Small question to the class. When do you think the impurity is maximum in a data point? In a given data set, when will you find the impurity maximum? How will you determine that when is the impurity maximum? Some answers have come in. Saurav is saying that root node initial case. Samrat is saying when all the points belong to the other class, non-predicted class. Vikas is saying when all classes are equally present. Correct. We'll take Vikas's answer. Right? See, I mean, when you have, let's say two classes, two class problem I'm talking about. When both the classes are equally present, that is when maximum impurity is there. Right? So let's say in your in your data point, you have so let's say you're consuming water, and this water has equal volumes or equal amount of water and soil in it. Right? Maximum impure. Right? By the process of filtering, what you will try to do is maybe the soil part. You will try to clear till the point there is soil in the water. Right? I think it's someone who has raised his hand. Yeah, I think someone raised his hand. No? No? Thought someone had raised his hand. Anyway. Okay. Samip is saying that the value is 0.5. Yeah. In terms of the proportion of the classes, whenever the value is 0.5, or again, see, 0.5 is for two class problem. For a three class problem, obviously it's 0.33, like that. That is when the impurity is maximum. When for the different classes, same number of data points are present, then it's maximum impurity. Samrat raised his hand. I don't know. I mean, the hands are getting raised, and then I think Samrat raised his hand. I'll just unmute him. Yeah, Samrat.
Yes, sir. So I was having some trouble with these things. So my question is that, like, it depends on the condition, right? See, whenever you are kind of putting some condition, like say I'm saying that, like, if temperature, if it's a monsoon, how many players are going to play in a given day, like that.
Mm-hmm.
So in that way, like, it may happen that the node is impure, like, for a positive condition, like we have the data, like we have the data of, say, we wrongly classified it to something like where there are 80 people who are going out to play and 20 who are not going out to play. But the right classification is probably 80 who are going to.
Samrat, I'll just stop you. Your voice is echoing, right? I'm not able to follow you. There's some kind of an echo in the voice.
Okay.
Yeah. Can you just probably come closer to the system and maybe speak once again?
Yeah. So I was thinking, like, while doing the classification, like this impurity, right? The ratio of the impurity, it depends on the condition also, right?
On what condition? I did not get that.
See, suppose we are classifying, like, on a
given... I'll make your this thing dilemma clear. See, the impurity is dependent on the target variable, right? If your target variable is homogeneous, doesn't matter how the feature is divided. Your feature might have several values which are not homogeneous. Forget that. If your target is homogeneous, if target class uniform, doesn't matter that how the distribution of the features are. It is going to be pure. Vis-a-vis, if your targets are pure or impure, but if your features, it might be pure or impure, but your target is not pure, right? There are different classes remaining out there. Then we have a lot of impurity, right? Okay, so that's what I was saying, that in a data set where all impurity reaches the maximum value when all the classes in the data have equal probability or present in the same proportion. Right? Okay. Let's try easily with the first example. So the first metric that we are going to take is something called as the classification error. Right? So let's look at this data point. Here we have 12 data points, which is in the parent node, or here it might be the root node as well. Of this 12 data point, you see that 4 data point comes here and 8 data point comes here. Right? Now let's look at the parent node. The parent node is having 12 data points. The classification error says that the classification error, which is a measure of impurity, is 1 minus maximum of the proportion of the different classes which are there. So basically, this will be 1 minus, in this particular case, maximum of, once again, just a, if I see the two classes which are present, right? So the yes class is 8 by 12. Yes class is 8 by 12. And the no class is 4 by 12. Right? So 1 minus maximum of 8 by 12 and 4 by 12, which is basically 8 by 12. Right? So 1 minus 8 by 12 will be 4 by 12, or 0.33. Right? So yeah, 0.33 is what we will get out here. Right? Come to this particular part. This particular part, I am having 4 data points, of which 2 are saying yes and 2 are saying no. So that means it is 1 minus maximum of 2 by 4, comma 2 by 4, which is 1 minus 2 by 4. So this is 0.5. From the class, can I have the classification error for the right hand side? For the right hand side, there are 8 data points in the right hand side. Can I have the classification error for the right hand side? Using the same formula, 1 minus maximum of the proportion of the two classes. Right? Why doesn't everyone try? Right? Everyone can try, and let's see what we get as the answer. Some people have already given me the answer. Samrat has already given the correct answer. Saurav has given the correct answer. Raj has given the correct answer. Snehal has given the correct answer. Samip has given the correct answer. Yeah, what about the others? Why don't you try? Very easy thing. Simple, apply the formula that we have out here. 1 minus maximum of the proportion of the classes which are there. In this particular case, 1 minus maximum of 6 by 8, comma 2 by 8, which is basically 1 minus 6 by 8, or the answer is 2 by 8, or 1 by 4, or 0.25. People who have not got 0.25, I'm sorry, I think Raj, you made some mistake. I overlooked that. So Raj, your answer was probably wrong. Right? The impurity is 0.25, not 0.75. Right? Okay. So proceed. Yeah. Right hand side, we have this one, 1 minus 6 by 8, which is basically 0.25. Right? Now come to one thing. See, let me come back to the example of the water purifier that we spoke about. Right? So once you have heated, let's say the iron guard or something like that, some kind of a new filter you have put in, you expect that the impurity which you're having out here, right, that impurity has got reduced. Now for this particular part, 0.33, that was 12 data points which were there. So 12 of 12 data point giving you this impurity of 0.33. But what has happened is that on the left hand side, 4 of the 12 has come in, right? And on the right hand side, 8 of the 12 data points, they have come in. So basically, 4 by 12 on the for the left hand side, 4 by 12. It's creating some issues. Yeah, 4 by 12 multiplied by the impurity which we had out here, which was 0.5, and then on this hand side we had 8 of the data point coming in. So 8 by 12 multiplied by the impurity which you had out here. I think it was 0.25. Right? Basis on that, see what we are getting. Yeah. Basically, we are getting the value as, what does this mean is that whatever was my impurity at this particular point, using this temperature variable, I have not been able to reduce the impurity any bit, right? So whatever was my impurity earlier, now the same impurity is there. That's why this change in impurity is 0. Probably temperature is not a good variable in this particular case for doing the splitting, right? So again, what we need are those variables which probably will make maximum change in the impurity. So initially I might have a lot of impurity, but after putting in on those interventions, my impurity, overall impurity should reduce, right? Impurity reducing means that probably more and more kind of a homogeneous classes is what I'm having. That means the impurity will get reduced, right? So if here my impurity value was very less, right? Impurity value was very less out here, impurity value was very less out here, let's say 0, 0, then probably I have been able to significantly change the impurity after I had split on this temperature class, right? And that is what we aiming. Some question, let me have a look. So Vikas is asking, why does the equation assume 1 minus max? Does it assume that the classification error will be less? Could it also be 1 minus mean? No, Vikas, I mean, again, how the classification error been determined is the maximum amount of impurity that we are taking, right? So again, whenever I am taking the impurity value, so these different impurity values which are there, right? So maximum of that particular value is what I'm taking. Why I'm taking that? Because the complement of that this thing of that particular proportion is going to give me the impurity. So this particular part, the maximum of that proportion part, is basically giving me the purity value, right? And the complement of that is basically the impurity. So if I talk about the purity part, it is basically maximum of that particular proportion. Kavita is asking that how did we get 0.33? Kavita, we had discussed this in the very beginning. For the root node, here what we calculated was the classification error as 1 minus maximum of 8 by 12, comma 4 by 12, which is basically 1 minus 8 by 12. 8 by 12 is basically, I think it is 2 by 3. So 1 minus 2 by 3 is 1 by 3, which is 0.33. Okay, Shankar has a question. Shankar is saying, is it maximum or a summation? I did not get your question, Shankar. Let me unmute you. Yeah, Shankar, I've given you the permission.
Yeah, hello.
Yeah, you're audible.
So the formula says 1 minus max of P I upon T.
Right?
So here we are deducting 4 by 12 into 0.5 minus 8 by 12. So are we taking all the instances or the maximum one?
No. So first I'm finding out all the instances. So here the
Okay.
two instances which I'm having are 8 by 12 and 4 by 12. And then of those two instances, or again, there can be 10 instances as well. I'll be taking the maximum of those instances.
Okay.
Right? Okay. What we get as the change in the classification error out here. So classification error is one of the metric that we use. Probably the most easiest metric, easier to understand, easier to calculate. But again, it has some limitations in the sense that sometimes it is not able to do the classification properly. Right? Okay. Let's try out a different metric, one which is very popular, called Gini impurity. So by the way, the classification error metric, it comes from the theories of probabilities, right? That is where it is having the Gini impurity. It has its root in econometrics, and this is the default impurity metric, which is there in Python, right? In Python, if you are using decision tree, and if you don't specify that which particular error metric you're using, right? Then by default, what it will do is it will use the Gini impurity, right? Okay. So how do we measure Gini impurity? Right? Simple. Once again, it's a entity which will find out the amount of disturbance within the data. See, all these impurity measures, be it the classification error, Gini impurity, we talk about the entropy also, finds out that how heterogeneous the data are, right? Gini impurity also one of the same pieces. And what it does is that it sums up the probability of occurrence and non-occurrence of the different classes of the data. So, show you the formula. This is basically the formula, right, of Gini impurity. So what happens here in this particular, and it sums up over all the classes, right? So for the first note, the first class is 8 by 12, and the complement of it is 4 by 12. That's for the first part, which is yes. For the no part, it is 4 by 12 multiplied by the complement of that, which is 1 minus 4 by 12, which is 8 by 12. Or a simplified formula is this one. 1 minus proportion of all the different classes, square of that. So basically it will be 1 minus 8 by 12, creating some issues, square, plus 4 by 12, the square of this, right? Like that, the note comes up with a Gini impurity of 0.4. Now you might have some question as to, in the previous case, we found the impurity as 0.33. Here it is 0.44. So how do we interpret? See, the thing is that depending on what class of impurity measure you select, the impurity values will also be different. Right? So for example, whenever you're using the classification error, right? For the classification error, the impurity value of was 0.33. But again, for the Gini impurity here, by using the Gini impurity formula, we got it as 0.4. And by the way, you are never going to mix and match the different impurity values, the different impurity this metric. If you are using classification error, use classification error throughout. If you are using Gini impurity, please use Gini impurity throughout. Right? Don't say that, okay, first two nodes I have used classification error, then probably I'll be using Gini impurity. No, we can't do that. Right? Always stick to the same impurity. Can someone tell me what will be the impurity value at this particular node? impurity value at this particular node using Gini impurity. Using Gini impurity. Using Gini impurity, what will be the impurity value at this particular node? Just to help you solve it, there are these two classes. One is yes, another is no. Yes is 2 by 4 and no is 2 by 4. So basically 1 minus 2 by 4 or half squared plus half squared, right? Raj is saying a 0.5. Gaurav is once again saying 0.75. I don't think 0.75. Let me check. So basically it will be 1 minus half squared plus half squared. So half squared is 1 by 4. Half squared once again is 1 by 4. 2 into 1 by 4, which is 1 minus half, which is half. So again, Anand, Shanti, your answer is correct. Anand, Shanti, and I think also Raj, these answers are correct. It is 0.5 on the left hand side. Similarly, for the right hand side, what you can do is that will be 1 minus 6 by 8 whole square plus 2 by 8 whole square, whatever the value comes out. Right? Yeah. 6 by 8 whole square, 2 by 1 minus 0.375. Now that I have got the impurity values after splitting by temperature, can you tell me the amount of reduction in impurity which will happen? Reduction in impurity. The reduction in impurity which is going to happen out here. Reduction. So I'll help you calculate that in the root node, let's say, or in the parent node. This is the parent node. We had 12 data points. So 12 data points, which gave me an impurity value of 0.44. So 12 by 12 into 0.44. Now, after I did the split on temperature, 4 data points have come on the left hand side. 4 by 12, 4 of those 12. And 8 of those 12 has come out here. Right? 4 by 12 and 8 by 12. Now, what has happened is that of those 4 by 12, the 4 by 12, they are having an impurity value of 0.5. 8 by 12, they are having an impurity value of 0.375. Right? So the original impurity value, which is 0.44 minus 4 by 12 multiplied with this, and 8 by 12 multiplied with this taken together will give the final impurity value. Right? And this, by the way, is 0.02773. So you might have seen that with the original value, the first one, the classification error, we did not get any change in impurity. But yeah, using this Gini impurity formula, we saw that giving, if we use temperature, there is some kind of a reduction in the impurity that we are able to get out. Like that, what we are going to do is, with all the different variables, we are going to calculate the change in impurity which is there, and wherever the change in impurity is maximum, right, we'll take that particular variable for week. And this particular principle which I talked about, that will hold true throughout decision tree. This simple principle, I calculate impurity, right? Then I select the feature on which I can probably make the split. If I split, let's say on feature A, right? I see the different classes which are there, calculate the impurity values from them, and find out the change in impurity which I've got. Right? For feature B, once again, I do that. So like this, once we compute for all the different features, what is the change in impurity which we have achieved? The feature which gives us the maximum reduction in the impurity value, that is the feature which we take for the splitting. Right? Okay. That was the Gini impurity. And then the other one which is there, which is by far the most popular, it's called the entropy. Right? The entropy is probably the most powerful splitting metric amongst the three that we spoke about. So for people who have a background in physics, so entropy, what entropy measures is the amount of restlessness or turbulence in the molecules, right? If you remember back in your class 12 days, right? Once you heat up, once you heat up a particular vessel, what happens is the heat produces a lot of disturbance within the molecules, and that's why your utensil gets heated up. Similarly, if you cool down the utensil, then what happens is the molecules don't strike against each other, so the value is lesser. That particular principle is being used in data science, coming from the physics. And here, entropy, what entropy does is that it controls that how much of randomness or how much of a disturbance is there in the different values, right? In case of entropy, what it does that once again controls the split in the data, right? And then generally it will range between 0 and 1. If it's 0, which means it is completely pure, right? All the members belong to the same class. If it's 1, then there are equal number of all the different classes completely impure, right? How do we calculate entropy? This is the formula for the entropy. So entropy is the proportion of the values multiplied by the log to the base 2 of the proportion of those values. By the way, log to the base 2 applies when you are having two basically decision nodes, right? Two classes you're having. If you're having more than 2 classes, let's say 3 classes, 4 classes, there if you're going to use log to the base 2, then the entropy value will probably not be limited to 0 and 1, basically exceed 1, right? So what you can do is you can use log to the base the number of classes that is there. Otherwise, if you use log 2 also, that's also fine. But again, in that particular case, the value will probably not get throttled at 1. It might get more than 1, right? So again, if you see for the first root node, here the entropy will be minus 8 by 12 into log of 8 by 12 plus, minus 4 by 12 into log of 4 by 12, right? Okay. So in this way, if we just do this thing, so this is the impurity at the root node, 0.9183, right? Very close to 1, right? Very close to 1, which means a very impure node, right? Come to this one. Can anyone tell me the value of this one, the impurity value of this one from the formula that we just did? Impurity value of this one using entropy. Using entropy, can you tell me the impurity value of this one, the left hand side? Anyone? Left hand side, the entropy value. Anyone? Cora gave the answer 1. Yes, Cora, that's correct. So that is minus half log of half. Once again, minus half log of half, right? So log of half is basically 2 to the power minus 1. So basically minus half, plus half plus half, which is 1. Maximum impure, right? We have 4 data points, of which 2 belongs to one class, 2 belongs to another class. Saurav has a question. If there is more than one class, then can we use chi-square metric that we discussed in last class? See, Saurav, I mean, irrespective of the number of classes that you have, you can use any one of this. You can use any one of this. You can use the chi-square, you can use the classification error, you can use Gini, or you can use the entropy. Doesn't matter. Any one of this you can use, right? Okay. So again, entropy for the left-hand side, as I said, is 1. For the right-hand side, if I calculate the entropy, that will be 0.8113, right? Same formula they have applied. If we calculate the change in entropy once again, So this is the change in entropy, 0.441, right? If I by temperature, I see some kind of a significant reduction, the impurity value which we get. Now, what we'll do is not only the temperature, we'll split on all the other variables which are there, right? Or on all the other variables which are there, we'll make the split, and the variable where we have got the maximum reduction in the impurity value, right? So all these are impurity values, 0.9183, 1, 0.8113. Wherever the maximum reduction in impurity there is there, that will be the variable for splitting. Right? Fair enough? Let's take up a. Okay, so this is a very important question. Why entropy is working better compared to the other measures? So if you remember your machine learning one, right? One of the several measures which we measured the efficiency of our algorithm was the ROC, right? If you remember, if I draw the ROC curve for classification error, entropy, and a Gini index, right? This is how what we get. For the classification error, it is a triangle. A triangle, if you remember your class 9 mathematics, it covers 50% of the area of a particular square with the same base, right? So classification error will be able to help me out only in 50% of the cases. Compared to that, if you see the Gini index is having a flatter bulge for the ROC. That is having a better predictability, right, compared to classification error. If you look at the entropy, so entropy, the shape is almost like the Gini index, but again, it is more bulgier, right? So in that particular case, the entropy is something which will be having the maximum ROC, right, value, or sorry, maximum AUC value, area under the curve. And that's why the entropy generally is a better metric compared to the other two that we see out. Right? Okay. Some question, no, good. Okay. Again, there is also another way which we call as the information gain, right? What we discussed out here. So entropy we take at the parent node minus the proportion of the data and the entropy at the childs, right? So that is what we out here. Right? So Kavita is having a question. If entropy is better, then why we use Gini index? So in Kavita, it has to do mainly with the way which the calculation happens, right? Think of the entropy formula in itself, right? Entropy formula in itself, log calculation, all those things, right? It requires a lot of computing progress, right? Again, that's one of the reasons why which entropy is being used. But again, otherwise, see, if you see, as I said, that all this error metric that we spoke about, be it the classification error, be it the entropy, be it the Gini index, it has its root from one particular branch of science, right? Classification error came from the theory of probability, Gini index came from econometrics, entropy came from physics, right? So they have used their own ways of defining what is instability or unrest when it comes to data classes, right? So I mean that's one of the reasons why these different classes are being used. So again, I have told you that which one has the best performance measures. If possible, yeah, go ahead and use entropy. By default in Python, the Gini index is implemented, but again, you can Python to use entropy as well. We'll use entropy, give the particular command, right? Okay. So let's take the first algorithm, right? So again, all this time the ID algorithm we spoke about, there's so many other algorithms, right? ID3, C4.5, C5.0. Let's take the ID3, right? Also one variant of the CART algorithm which is there, right? One of the advantage with this algorithm is that it can take more than 2 classes, right? Some algorithms like the CART algorithm, the classification and regression tree algorithm is not able to take more than 2 classes, but here this one is able to take more than 2 classes. The guide algorithm that we spoke about, right? The guide algorithm that can also take more than 2 classes, right? It can take multi-classes for finding out the. So what we will do is we will basically continue with the splitting until and unless we have reached some kind of a homogeneity. Let's take this particular example. So here, this is a problem, very small problem. There are 10 data points which you are having. The gender is given, the car ownership of that particular customer is given, the travel cost which the customer prefers, that is given, the income level of the customer is given. And based on that, you'll have to find out whether the customer is going to use transportation mode, which is bus or car or train. My question to the class, that for the target variable, how many classes are there? That's the first question. For the target variable, how many different classes are there? 3 classes. Everyone is saying 3 classes, and you're correct. It's 3 classes. Okay. The second question is, what is the proportion of those classes? Proportion of those classes. Proportion of those classes. Proportion of those classes data set. Anand is saying 4:3:3. So again, I'll probably, yeah, Saurav has given me the answer. 2/10, 3/10, and 3/10. That's the proportions which we have having. Kavita has also given me the correct answer. Bus is 4/10, car is 3/10, like that. Right? So now that you have understood this, let's go ahead and apply whatever we have learned and see how we can deduct the rules from this data set as to what kind of transportation mode will a particular customer take. Right? Proceed with that. So as you can see in the root node, probability of bus is 0.4, probability of car is 0.3, probability of train is 0.3. Okay. One very small question which I have. So let's say that these features were not given to you. These attributes were not given to you. You only have the target classes which were there. And if someone asks you that, okay, for a random customer, what is the preferred mode of transport? What will be your answer? For a random customer, what will be your preferred? What's the preferred mode of transport? What will be your answer? All has given the correct answer. It's going to be bus, because again, we are going to take the maximal class. The mode is bus, like mode in terms of mode of the this thing. Target variable is bus. So that's why it will be taken. The bus will be taken. Okay. So you have rightfully answered the first question. My second question is that, let's say all the attributes are given. All the attributes are given. And so you, as you understand, in the root node, all the attributes along with the target class is there. But let's say I have decided that I am not going to take the decision tree, right? I am going to take the decision in spite of having all these attributes. Still, whatever data is there in the root node, I'll go via that. Then once again, you are going to take the maximal class once again, and the answer is going to be bus, right? That's the scenario when I have not done any splitting. Now let's see how we can do the split. These are the different 3 probabilities which is there. Bus 0.4, car 0.3, train 0.3. Right? So classification error at the root node is 1 minus maximum of 0.3, 0.4, 4 and 0.3. So which is 1 minus 0.4, right? So 1 minus 0.4 is 0.6. So that is the classification error at the root node, right? Similarly, the entropy at the root node is minus 0.4 into log to the base 2 0.4 minus 0.3 log to the base 2 0.3 minus 0.3 log to the base 0.3, which is coming out as 1.571. My question to the class, we just had discussed that the entropy value will lie between 0 and 1. How come it is 1.57? Have we made some mistake? How come it is 1.57? make some mistake. Once again, people have given the correct answer that yes, because we have taken log to the base 2, that's why we are getting the value as more than 1. By the way, it is not incorrect. So Saurav is saying that it is incorrect. It's not incorrect, Saurav. You can very well use log to the base 2. That's pretty standard. But what will happen is, because of multiple classes, you actually get the value as more than 1. If you would like to keep it between 0 and 1 itself, then use the log to the base of the same number of classes. So if you use the log to the base 3 out here, you'll find that it will get throttle between 0 and 1. Right? Okay. And then the Gini index is 1 minus 0.4 square, 0.3 square, 0.3 square, which will give you 0.66. Now, one thing is that all the 3 error metric are giving you 3 different values. In terms of how to interpret the value, see, one thing holds true is that if you're having homogeneity, then the error will be 0, right? Irrespective of whatever metric you're using, the closer the value is 0, lesser the impurity is there, right? The more the value is, right, 1 or more than that, higher the impurity values are there, right? Now we need to take a decision that how do we do the splitting, and for doing the splitting, I have this gender, car ownership, travel cost, and income level. So let's see how we can do this splitting. So let's say that I have split based on the travel cost. If I split based on the travel cost, I have 3 different travel costs. One is cheap, one is expensive, the other is standard, right? So I've randomly selected that, okay, let me work on the travel cost variable and do the splitting. Now, see one thing, that once I have split based on this travel cost, what has happened is that for the travel cost expensive, I have attained homogeneity. For the travel cost standard also, I have attained homogeneity. Right? How do I know I have attained homogeneity? Because again, there are no other classes. Right? And if you calculate the impurity value, irrespective of whatever impurity value that you are using out here, the impurity value is 0. Right? Entropy, Gini index, classification error, all the 3 are giving 0, 0, 0. Right? For the travel cost expensive and the travel cost standard. Right? So already by splitting on travel cost, right, there are 2 nodes which have completely attained homogeneity. The only problem is this one, where we still don't have the homogeneity, right? See, if I stop it at this particular point, right? Okay, once again, I'll ask you this question. Let's say I have stopped my decision tree at this particular point. So what is the accuracy of this particular decision? So I split the decision tree to one level, right? And this is where it stops. What is the accuracy of this model? Accuracy of this particular model. Samrat has already given me the answer. Let me check with the others. Samrat has given me the answer, which is correct answer. Saurav has also given me the answer. So Saurav, the answer is incorrect, unfortunately. Check it out, you'll find out it's incorrect. Kavita has given the correct answer. Anand, the answer is incorrect. Okay, anyone else? I'll discuss obviously, but yeah. Any other answer? See, these are very simple maths that we are doing, right? But again, once you get that clear now, what will happen is, again, you'll no longer remain the person who probably has to use only Python to give some answer, and you're not able to interpret that. Here we are actually discussing how you're interpreting the answer. Anyone else? I think Kavita and Samrat has given me the correct answer. Saurav, yeah, I got the correct answer from you now. Saurav has also given the correct answer. Anyone else? Anyone else? Vikas, answer is incorrect, unfortunately. Answer is incorrect, Vikas. Okay, let's come to the explanation, right? Anyone else would like to give the answer? What happened to the other people? Shayanti and the other people, right? Very simple calculation, very simple calculation. See, I have this 10 data point, right? I split the data based on this travel cost cheap, expensive, and standard. Now, once this has happened, you find that of those 10 data points which are there, if I stop at here, what will happen is that here, all the three of the three data points would have been correctly classified. All the 2 data points out here are correctly classified. Here, of the 5 data points, 4 are correctly classified, right? So in total, out of the 10 data points, 9 are correctly classified. 1 data point is correctly classified, basically this train part. Why? Because again, if I stop here, I'll go with the maximal class. So travel cost cheap. If I don't split this further, my answer for this will be bus, and in this particular case, be one member which will get an incorrect answer. So that's why 9 by 10 or 90% is the accuracy of this particular model. Right? Fair enough? Okay. What I have after doing my question to the class, is my problem solved or we are missing out something? Is the problem solved or are we missing out something? Again, people are getting restless. They're asking for some break. Let's just complete this small piece and then we can probably go for a logical break of 10 minutes. Right? Okay. Is my problem solved or something more is remaining? Is my problem solved already? Yes, no, maybe. Is my problem solved? Kavita is saying not solved. No, no. Saurav is saying depend on stopping criteria. That's a good answer, Saurav. Kavita is saying still has heterogeneous. Yes, it still has heterogeneity. That's why there is still scope to go further. Now, Saurav gave a very interesting answer. That depends on the stopping criteria. Because also has also given the same answer. If the benchmark is that the accuracy is less than equal to 90%, we are good. Then we are good. We can stop here because again, my accuracy is 90%, right? But again, if I'm desiring that more than 90% accuracy will be there, probably I'll have to split further. So let's do that. Let's do that. Okay. So one thing which we did was, okay, this was the impurity values after doing the split we have done. And the earlier impurity values we had at the root node 0.6, 1.571, and 0.66. So what we also need to do is we need to find out the change in the impurity we have got, the change in the impurity. By the way, this particular part, 3 by 10 of the data is giving 0 impurity, 2 by 10 of the data is giving 0 impurity, 5 by 10 of the data is giving an impurity of 0.320 for gene index, 0.200 for classification error, and 0.72 for entropy. So let me take the classification error. So at the root node, my classification error was 0.6. Here it is 0.2, but for only 5 by 10 of the data or half of the data. So half of 0.2 is 0.1. 0.6 minus 0.1 will be 0.5. If I tabulate half of 0.6 is 0.1. So 0.6 minus 0.1 will be 0.5. My bad. So now I have found out the change in the impurity for each of the three metric: entropy, Gini index, and the classification. The change in the impurity value for each of this. My question, once again, I'm asking the same question. No one has given me the answer. Is my problem solved? Some people said no, right? Because it is still heterogeneous, right? But again, still at this particular level also, my problem is not yet solved. What are the steps which I have missed out? What step has been 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 missed out? Saurav is saying to check on test data. Not really, not really. Right? What is that which we have missed out? We have found out that if we split based on the travel cost, these are the impurity values, change in impurity, all those things we have found out. Is there something which have I completed the process? Snehal and Kavita has given me the answer. Other attributes are not considered. Saurav has also given the, we have to check on the other features as well, correct? We have just got this from one of the attributes. We have to do this for all the attributes. Anyway, I'm not going to the calculation for it. I think how it is being done, we have already discussed, right? This is what we are getting. It is split by the gender. It is split by the car ownership. It is split by the income level, right? These are basically the change in the impurity values, change in impurity in the different cases. Change in impurity in the different cases, right? What I need to do right now is I need to do a comparison. Here is the comparison, right? So the change in impurity or the gain value, whatever you might say, for the gender, it is 0.125. For car ownership, it is 0.534. For travel cost, 1.210. For income level, it is 0.695 if I use Entropy. If I use Gini index, for gender, it is 0.060. Car ownership, 0.207. Travel cost, 0.50. And income level, 93. Right? For the classification, it is there. My question is that on which variable am I going to do the splitting? What do you think? On which variable should I take for doing my first split? Anand, the answer is not correct. Snehal, not correct. Vikas, not correct. Saurav, not correct. Only Kavita has given me the correct answer. Only Kavita has given me the correct answer. Only Kavita has given me the correct answer. Only Kavita has given the correct answer. None of the other answers are correct. Once again, let me repeat what we said, right? So what we find out is that what was the impurity value at my root node? Vis-a-vis, whenever I have split by each of these variables, right? Be the gender or the car ownership or the travel cost or the income level, what are my impurity values? These are the impurity values which I have got, right? If I split by the gender, right? Impurity values, if I split by the income level, right? Now I need to find out the change in the impurity values, right? By what amount the impurity value has changed, right? And my objective is to find out where the change is the maximum, right? Okay, so in that particular case, find the change in impurity is maximum if I split by travel cost. So whatever was the impurity at the root node, vis-a-vis whatever is the impurity after doing the splitting, that is maximum out here. So maximum amount of impurity I will be able to remove if I split based on the travel cost. So that's why travel cost is the first variable for splitting, right? Only I think Kavita had given me the correct answer, right? Everyone got the idea that why it is travel cost, right? It has resulted into the maximum reduction in the impurity. So yeah, Caution is asking that can I repeat it once? Yeah, sure, why not? So if you see that I had at my root node some kind of impurity. Let's say at my root node there was impurity value of 1 was there. Now I have done some kind of a splitting, right? So let me show you the first one. It will be easier. So here, this was the impurity values at the root node. 0.6 if I take classification error, 1.571 if I take the entropy, and 0.66 if I use the Gini index, right? And then we had taken this one example where we split by the travel cost. If I split by the travel cost, then for this particular section, impurity value has become 0. This particular section, impurity value has become 0. And this particular section, there is some impurity value, right? This particular section is accounting for 5 of the 10 data points which I had. The rest 5 is giving me 0. This 5 of the data points is giving an impurity value of 0.2. So its contribution is 5 by 10 into 0.2, which is 0.1 for the classification error, 5 by 10 into 0.320, or half into 0.320, which is 0.160 for the Gini index. And again, here it is half of 0.722. Now, if I take the change in the impurity value which we had, this is the change in the impurity value which I'm having. So for Gini index, it was 0.660 minus 0.160, which is 0.5. For classification error, it was 0.6 minus 0.1, which is 0.5. And likewise, we have also got for the entropy values, right? So Anand is saying that if we have already split by travel cost, then how again we can split by travel cost? No, Anand, we are not splitting by travel cost. What I only said is that we have already checked only for the travel cost. We also need to check for all the other values. All the other values. And Caution is saying, so the values give the reduction in error, not the error, right? So yeah, I mean, if the error value is lower, the better. Reduction of error, the higher, the better. If these error values are low, right, which means that this split is working correctly, the reduction in the error should be maximum. So just think of it, right? You are checking the TDS of your water, right? Initially, a very high TDS is there. And after applying some kind of filter and everything, the TDS of the water has become very low, right? And you are checking multiple filters. So whichever filter has given you the maximum reduction in the impurity, you are going to take that particular filter. Same logic applies out here, right? Okay, so here travel cost was my first variable based on which I'm going to do the splitting, right? So yeah, after I have done the split based on the travel cost, as I see that this one has become homogeneous, travel cost expensive, travel cost standard, both of them, they are homogeneous. I don't need to split it further, right? Travel cost expensive, travel cost standard, homogeneous, no further splitting required. Only travel cost cheap where I need to further work on this, right? So here is my attributes right now. My attributes are gender, car ownership, and income level. And this is the output class. I don't need to take the other 5 because they have already become homogeneous. I don't even need to consider them. Here in this particular part, once again, if I take this particular data, these are the impurity at this particular data. So right now, this is right now my new parent node. And these are the values of the impurity which we are having, 0.722, 0.320, 0.2, based on the defined metric. Once again, I'll do a split based on the other variables which are there. So Anand, right now you can see that I am not using the travel cost anymore. The other 3 I'm using, which is the gender, the car ownership and the income level, right? And this is the reduction that we are getting from this particular table, the one on the bottom. Can you tell me that on which particular variable we are going to use the split? On which particular one are we going to split on this time? Farah, the interpretation is wrong, Farah, once again. Farah, the interpretation is wrong. For the others, as of now, I've got the correct answer. Anand, answer is correct. Saurav, answer is correct. Kavita, answer is correct. Okay, so once again here, I'm going to find out that which of these variables, be the gender, be the car ownership, or the income level, has given me the maximum reduction. By the way, this one has given me the maximum reduction. So I'm going to split this time based on the gender. Right? Based on the gender, if you see, once I've done splitting based on the gender, for the males, I have already reached homogeneity. For the males, no further splitting is required. And for the female, by the way, right, once again, there are some ambiguity still there. Bus or train, that's the ambiguity. So what we can do is, for this particular part, we might do the splitting based on the car ownership or the income level, whatever. We might do the splitting. And here, because only 2 data points are there, and we can either split on the car ownership or the income level. But here is how my tree looks like right now. So travel cost standard, always go via train, no issues. Travel cost expensive, always go via car. Travel cost cheap, that is where we had 5 data points. And there, if the gender is male, clearly they're taking a bus. If the female is there, we need to split further. If we take the splitting again, as I said, that you can take either the car ownership or the income level, any one of this you can do. Same answer you'll get. What I'm getting. By the car ownership, if the female is not having a car, then she will prefer a bus. If the female is having a car and a cheap mode of transport, then she is going for a train. So my decision tree has been created. Now my question, quick questions. Okay, what will be the travel mode for a female who prefers a standard mode of travel? The information is there in front of you. What will the travel mode for a female who's using a standard mode of travel? The answer is train, as people are rightly saying. I think some people they are asking for this break. I think you had this IAs before this. Let's have this break. Let's have this break. We'll start from here. Right? Should we have a break? We are done. We are done with this particular part. The explanation part, the mathematical part is done. Should we have a break now? We have a break. Okay. So it's 8:35 in my clock. It's 8:35. Let's come at 8. So it's 8:36. Let's come at 8:48. Let's come back at 8:48 and continue with the part. 8:48. Right? I'll just pause the sharing. We'll come back at 8:48. 8:48. Caution is asking the mathematical calculation in Excel sheet with formulas if you are having. So again, I think once you go through the slides, the mathematical calculation is given there, but yeah, that can be done. Not a big problem. Not a big problem. come back slowly. Okay. Got your necessary break. Okay. So yeah, we were out here and we were discussing about the decision tree that we have created. See, as you can understand, first of all, the final outcome that very easy, right? Decision tree. The decisions are pretty clear. The kind of a rules which can come out of this also pretty easy to interpret and use. So it follows some kind of a if then else kind of a rules. If you see, if the travel cost is expensive, car. If the travel cost is standard, use a train. Or if the travel cost is cheap, then ask for the gender. If the gender is male, uses a bus. If it's female, then probably take some variables. Samrat has some questions, so let me come to Samrat. Yes, Samrat.
Thank you, sir. So, sir, actually, we have seen in regression and like linear and logistic regression that we are fitting one function and we are kind of reducing the errors on top of it. So, in this case, in decision trees, we won't be able to form a problem like a curve fitting problem, right?
I did not get your point. What do you mean by not able to form a curve fitting problem?
So in an see like in logistic or in linear regressions, we were fitting a plane or we were fitting a line through the data points, right?
Right.
So here in case of decision tree, we could not form a plane or we could not form a line, right? So we have these conditional approaches.
Not really. Not really. See, at the end of the day, when you're talking of this approaches, conditional approaches, finally that might also lead to some kind of a plane or a curve. Right? So when you plot those points, the decision region, that might also lead to some kind of a plane or a curve. See, one of the advantages of decision tree compared to the other ones is that decision tree, it is a non-parametric method. It doesn't make any kind of assumption about the underlying function. So say, for example, a linear regression. The underlying assumption is that it has to be some kind of a linear relationship, right? But again, in a decision tree, you can probably have a different kind of a structure in the decision boundaries. That is possible. That is possible, right? Again, finally, that is going to be some kind of the other hyperplane. It might not be straight. It might be curved or something like that. But yeah, it will create some kind of a decision boundary. Only is that if it's more than 2 dimension, you may not be able to visualize that.
So is it possible to kind of formulate a equation for a decision tree?
See, again, at the end of the day, why do you want an equation? Because your final objective, let's talk about the objective. The final objective out here is not to get some kind of equation, but actually to do some kind of a prediction. Prediction of a class, or be it the prediction of some kind of a number. And both of those particular objectives are being very much satisfied out here. So why we should even bother with a particular whether there is the equation or not?
Sir, actually, to be honest, sir, I am thinking of this problem, of some of the problems which I am solving. Maybe it is a little bit out of context here.
We'll come to the discussion. As I said, that we'll spend some time out there, right? But again, at this point in time, it's a non-parametric method. So yeah, it can take multiple kind of different shapes or formats of the decision boundary. Okay, there's some other question. Okay, so Anand is asking, when do we use chi-square vis-a-vis impurity calculations, right? So again, Anand, in this particular case, I mean, see, it depends on what exactly you're looking at, right? So chi-square kind of solutions we generally use for classification problems, right? But this particular method, which I talked about right now, 4.5 method, which is there, that you can use classification as well as regression problems. Right? So those are different ways or different methods in which you can find out the decision. For example, the chi-square method. Chi-square method, it has its root in the statistics world. As I said, that the different fields, they came up with their own metric, which they can create this decision. Yeah, want to use chi-square? Yeah, go ahead and use chi-square. Who's stopping you? Right? Okay. But here, at the end of the day, have some very simple tree-like structure which can be easily interpreted and put into account. Right? Okay. Now, these are the reasons for the popularity. No domain knowledge required. Very easy to understand. Right? Can be used for data exploration. Data cleaning is not that much required. Very less data cleaning is required. See, for example, come here, right? I built this tree, right? Now, these variables which are important, right? Here in this particular case, the variables which were important was this expense, this travel cost, the gender, this car ownership, right? These are the variables which are important. Now, even if some of the variables, they had missing data, right? It doesn't cast too much of a problem on my final result. If those variables itself are not really significant, then in any case, those are not required. If these variables are significant, yeah, one way in which you can deal with that is probably you can give it some kind of a unknown kind of a level unknown. Or otherwise, what you can do is if the variable, if the values are missing for variable which are significant, maybe you can try to take the mode, right? Because again, as such, if you stop the tree prematurely, so basically the class with the maximum maximum membership will take that. So likewise here also you can probably approach it the same way. But again, the thing is that the amount of data cleaning required is pretty less, right? Data type is not a constraint, can handle numeric variable, categorical variable, binary variable, all the different kind of variable. But this particular point has to be taken with a pinch of salt. So, though decision tree, for decision tree, the data type is not a constraint, both for the features as well as the target, right? In the target also, it can take up both numerical problems as well as classification kind of problems, right? For the features also the same. It can take numeric values as well as categorical values. But for numeric values, the problem is there. What happens is that you can't have one branch each for the different numerical values, right? Internally, what it does is that for the numerical values also, it creates some kind of a categories. So let's say I'm taking the marks of students in the class and the marks are between 1 to 100, right? So maybe internally what it will do is it will check for the distribution and then it will find out, okay, my one class will be students with marks more than 70. Other piece will be students with marks, let's say, less than 30, between 30 to 70. So like that, it will create different classes and go on with the same calculation is there, right? Gaurav is having a question, I think interesting question. Does feature selection help decision tree, or it can select feature based on the different metric on its own and feature selection does not have a role? So again, sort of the whole part of using this impurity metric and from that filtering out the irrelevant features, the feature selection method. It is the feature selection method that we are using. So that's one of the part in constructing a decision tree, right? So using those methods by finding out the impurity in the features, right? And then calculating the reduction in the impurity, that particular step will basically help you select the features. Okay, so the follow-up question from Saurav is that you don't have to remove the features by us when using the decision tree. So again, one of the implicit methods in the decision tree is the feature selection part. That's the essential state there, right? So yeah, see, when we come to the model selection part, right, this is also something that we are going to discuss. What are the different kind of model selection methods? And here in the decision tree, what happens is that it's a step for constructing the decision tree. Okay, so Kavita has a question. For missing numerical variable, we should replicate with the mean or median. Yes, same thing that we have done, the same thing out here, right? We can replace that with the mean, median, or again, if you are creating some kind of a different categories for the numerical variables, you can also use the mode of the categorical variable. That was Kavita's question. There are some questions from Saurav as well as Samrat. Let me unmute first Saurav. Yeah, Saurav, please.
Yeah, good evening, sir.
Good evening. Good evening. Tell me.
Yeah, my question is actually, I use the random forest exhibits kind of trees for the real life problems.
Right.
But like there is something called feature importance, you know that, right? Like it
Right.
plays the features automatically by its own, and we don't do any effort in there actually. So
Right.
question is like, you know, if in real life problem out of say several features, so we don't select any features, we leave it to the trees. I mean, random forest or whatever, right? I mean, if we do it by
not really. So this whole point of you finding out the impurity values itself comes in the feature selection part. So what we do is whichever feature is having a maximum reduction in impurity, that's the topmost preferred feature, followed by the other ones which are there, right? And that's the methodology that we use. In fact, in the hands-on problem that we are going to do with the decision tree, this particular part will be actually covered out there as well. So I'll show you that how we are getting the different impurity values, and from there how we are constructing the different features.
So my question is like the model does it for us, right? We don't have to do it manually. Like we leave it to the model, give input to the tree, and then it comes up with the feature importance. So we don't bother about like
it comes up with the feature input. No. So again, when you're saying that the model is doing it for us, so the model also follows the same step. It is calculating the importance of the feature, and based on the feature, which is most important, it is basically using that to do the splitting.
Correct, right? Sir. I mean, I understand that, sir. My question is like, we don't have to do any manual thing. Say, if we put in regression, I know if we do feature selection of our own by say doing a pair plot or something, we can remove some other features by ourselves, and then we feed those features in the model. Or we can do the in forward or backward filling method to select the features in
I got your question.
Regression. Yeah,
I got your question. Yeah, so here the feature selection is an implicit requirement of building the model itself.
Correct.
Right. Okay, thank you. Samrat is having a question. Yeah, Samrat. Yes, Samrat, I think you had a question.
Yes, sir. So basically the same thing. So like suppose we are given a problem and we need to figure out say some regression or classification type of problem. So what feature selection we do for like suppose we are starting with a logistic regression. Now if we figure out the best features for logistic regression, the same thing are not applicable for decision tree, right?
No. If you think it that way, see, in logistic regression, what you do, like for any regression problem, whenever you're fitting that particular line or a plane, right? You can you find out the p-values of the different features which are there.
Yes.
Right, and whichever feature is having probably the highest p-value, right? So that is the one which you're considering.
Yeah.
Right. So again, I'm sorry. I said the other way down. Whichever feature is having the lowest p-value, whichever feature is having the lowest p-value, that's the one which you're considering.
Correct, sir.
Right. So then what you're doing out there is the p-values, whatever you're getting out there, those p-values you're arranging in a ascending order. Correct? Okay. So and the one which is having a lowest p-value, that is the one which is the most important variable for your model. Here in this particular case of a decision tree, what we are doing is you are probably using the impurity values, and wherever for whatever feature the impurity value is probably the lowest, right? So lowest impurity value for a feature is basically getting the maximum reduction in the impurity. Lowest impurity value is leading to the maximum reduction in the impurity or maximum impurity reduction, right? So in that way also, when you have, let's say, 5 different variables, you're finding out that when you split by each of these 5 different variables, what is the impurity value that you get after splitting by each of the 5 variables? Whichever is having the lowest impurity value for that particular node or the maximum reduction in the impurity, that's the most important. Did I answer your question?
Yes. Yes.
Thank you so much. Okay. So this classification, as I said, it's based on the probability alone, right? So that's the good part of the thing. Okay. Now comes a very important part. It's called the overfitting and the underfitting, right? So if we come back out here, right? Here, when we have built this particular tree, this particular part was good. This particular part was okay. But as and when we finally went down the decision tree, the number of records which were there in these nodes became shallower and shallower. And then what is happening is that the tree is getting to some kind of a super specialization, almost to the point that it requires the exact values to make the prediction. Right? At this particular level, it was pretty standardized, right? Here for car and the this thing, the I think bus. So still in this particular case, for the bus, there was a 4/5 chance, right, of getting it correct. But again, when you have split it further and taken it down, so in the training data set, you're probably getting 100% kind of accuracy. But the thing is that since you have done a super specialization for the validation data set, that kind of a feature might not even exist. Those kind of a points might not even exist. And your model might become totally confused. So that's why if you are building a decision tree, you're getting to a point where you have probably just 3 or 4 points based on which you are making the prediction, not the best way of building the tree, right? So your decision tree will basically overfit the data. So in the sense that it will give very good results on the training data set, but you'll find that on the validation data set, it is performing very poorly, right? Okay. So how we can avoid this overfitting part? Very simple. That you prune the tree. Right? Again, if you have gone to a particular, let's say, park there, you find that the gardeners are there who are always cutting this thing bushes, trying to give it some good shape, right? Why? Because so that again, it fits properly and it doesn't grow too much where it leads to some kind of ugliness. Same for the decision tree as well. If you're having a tree of a very high depth, so one advantage is that at least on the training data set, you get 100% fit, right? So all this time we were discussing that, okay, after I do the split at 1 level, 2 level, what is the kind of accuracy that we are getting? Here, you'll get 100% accuracy of the training data set. Same will not be replicable for the validation data set, right? If you like make a super specialized tree, you find that it is suffering heavily when it's come to the validation data set, right? Then there are 2 methods to it. One is that where at the very beginning you say that, okay, I need this kind of a, let's say, height for the tree or this kind of accuracy for the tree, and beyond that I'll stop growing the tree. Otherwise, the other method is that you allow the tree to grow fully, and then after the tree is fully grown, then you start growing the tree, right? So post prune it. And then what you can also do is, rather than decision tree, as Saurav was trying to say, that maybe you can go for a forest, right? So what's a forest, by the way? What's the forest? What's the forest? How a forest is different from the tree? What's a forest? So forest, as Samrat is saying, Kavita, Saurav, as they saying, collection. Good. So what happens in a forest or a random forest in the world of data science is that we create decision trees, not many decision trees, but we don't fully grow the decision trees. We grow the decision trees only partially, right? We grow small, like bonsai kind of decision tree. And then, so you might have a question that, okay, professor, if you are building so many small decision trees, they will have the same parameter. That is where the twist comes in. When these small trees are being grown, what happens is, let's say that there are 5 features which are there. So you take out one feature at a time and build those different decision trees out there. You probably use a subset of the data and then build out those trees. So like that, you will get a variety of the tree, right? Even if those a small tree, just because you are using different feature subset, you'll get different kinds of tree. You're using different subset of the data, you'll get different tree. And based on that, a forest will be created, right? And once you get the forest, based on whatever are the most important variables. So let's say that you have built a forest with 1,000 trees, and this 1,000 trees, find out that what's the most important variable for those 1,000 trees, right? So let's say that 200 of those trees are saying that variable A is important. 150 of them, they're saying that variable B is important. So like that, once again, what you do is that you find out that which are the features which are coming as most important for the forest that you have created. And that's how you get the feature importance in a random forest, which basically answers the question which sort of had mentioned that, okay, how in the forest we have some particular kind of hierarchy, how that happens, how it happens. Some other questions. Okay, Samrat is having a question. In case of a single decision tree, would not it always overfit on training data? So yeah, Samrat, if you are growing the decision tree fully, chances are that it will overfit the training data. Chances are that it will overfit the training data, right? So why I'm saying the chances are that it will overfit. So again, in some cases, the data is probably it's pretty sorted. It's in a pretty good format, right? So let's say you are having 10 or 12 features in the data, and using 2 or 3 features only, you are able to get completely homogeneous tree. In that case, probably those 2 or 3 features are the ones were most important to create the tree, right? That case probably it will not overfit. But yeah, as and when you go on and create shallow trees, right? More and more depth you go, right? As the tree becomes shallow, right? Lesser number of records are there. That is when the overfitting problem comes in. Right? Got the point? Okay. Right. Okay. Now, how do I stop the overfitting problem? Right. So there are some parameters that you can control in a tree. One of the parameters, the first one is the split criteria. As I said that in Python, by default, it uses a Gini. But again, otherwise, you can use an entropy as well. Or again, if you want classification error. So you can give some kind of a parameter, this hyperparameter you can actually tune, the split criteria. The other is the maximum depth we have talked about. Rather than going the tree fully, maybe you tell that stop at 2nd level, stop at 3rd level, right? That's also another hyperparameter. The other one is the minimum sample split, right? Minimum number of samples required in order to split a node. Let's say in a particular node, you have said that, right? As I said that you don't want to create shallow trees. You said that minimum, if there are, let's say, 20 data points in this node, that is when I'll probably go for a split. I'll not go for a split if the number of data points in this particular node are less than 20. Other one is minimum sample. It's this minimum sample split and minimum sample leaf. It's a minimum sample. What happens is that you can specify that what's the minimum number of leaf nodes that are required. So let's say here you have given the minimum sample split as 30, right? 30. What will happen is that if there are 30 or more records, then this particular part will get splitted. But let's say, for example, here the minimum sample leaf you have given as 12, which means that each and every node should have minimum 12 records or more present, right? If it's less than 12, then that particular split, whatever has happened, will be invalid. It will go back. Now let's say this 30, which you have given a minimum sample split, was split as 16 and 14, right? So then as per the minimum sample split, right, you can't split this further because 16 records are there, minimum sample split says 30, this is 16, this is 14, so you can't further split them. This is fine. In terms of the minimum sample leaf, minimum number of samples in the particular leaf node, that has been given as 12. So both of these are satisfied, right? This one is having 16, this one is having 14. This, but come here. Here, let's say it comes after doing the split of this 30 nodes, this becomes 19 and this becomes 11. Then your minimum sample leaf is violated. Minimum sample leaf is violated, and in that particular case, this particular split itself will be invalid. So at that point, when we were at 30, we will not be able to split it further because after splitting, the minimum sample leaf condition has been violated. Doubts? Anyone? Doubts? So one, we had a minimum sample split, a minimum number of records we required to split, which is like, let's say, has been set off as 30. There are more than 30 records which are there, 30 or more records. We should be able to split that particular node, right? Here, let's say there are 32 nodes which were there. 32 node, if we can split as 18 and 14, perfectly okay. We can't split this 18 and 14 further because the minimum sample split, it will not allow us to split after 18 and 14. Come to the minimum sample leaf part. At this point, 18 and 14, it is fine with the minimum sample leaf part. But had this been, let's say, had this, let's say 24. 24 out here after doing the split and 8 out here. Though it satisfied the minimum sample split, it does not sample the minimum sample leaf because here it has come as 8, whereas the minimum number required was 12. So this particular split will become invalid and we will probably have to go back to wherever we were. Right? There's a question from someone. Okay, Saurav is asking that we should have any one of those, right? Or in order of preference, we can give more than one. You can give more than one. You can definitely give more than one. Right? No one is stopping you from giving. You can actually use all the 4. Split criteria, maximum depth, minimum sample split, minimum sample depth. All the 4 actually you can use. Right? Okay. So yeah, the illustration of what I was saying. Right? Minimum sample split, maximum depth, all those things. Right? Okay. So the not already discussed this. Rule extraction I've already talked about, discussed rule extraction. Right? So let me quickly come of a decision and how much time we have. I don't think we can do the regression tree today, right? I'll probably just talk about the issues of the decision tree and then we'll open the session for taking questions or discussion with the class. So issues in decision tree, continuous attribute, as I said, that though it can handle continuous attribute, but internally what it does is that those continuous attribute, it splits based on the different classes there, right? Using an appropriate attribute selection measure. Now, whether you are going to use chi-square or you are going to use Gini or this thing, entropy, there is no particular guideline for that. I've shown you some kind of a rule of thumb and again, some kind of empirical result which proves that the entropy will be best suited generally. But again, that's pretty empirical. Right? Like any other machine learning problem, so though this is robust to outliers and missing values, but still handling data with missing values, it always creates a problem which is there. And the other one is proving computational efficiency. Also, if you give some kind of a weightage to the attributes, that is also something which reduces the efficiency of a normal decision. Again, as you see out here, that for a continuous data, let's say it goes from 0 to 100, there are infinite number of possible values. In those cases, what we do is we generally try to see the distribution of the data, right? And try to make generally 4 or 5 different classes from the data itself. That's what we try to do. Okay. Kavita has a very interesting question. For attribute selection, we do need domain knowledge, right? Not really true, right? So for the attribute selection, what we are doing is we are doing it mathematically. We're finding out the impurity of the node, and whichever node is helping you reduce the impurity to the maximum extent, that's what you are using for the selection, right? And what you find is that the beauty is that this mathematics that you do, that you'll find it also is coincidental with the domain knowledge which is there. If you have the domain knowledge, well and good. Domain knowledge, and there also maybe you'll find that whatever domain knowledge is pointing to, the same thing is being pointed to us, to you, by mathematically as well. Right? But again, it might not always be the case which is there. Right? Okay. How much time we have? Not much. Not much. Just to give you an idea, we'll start this in the next class. What happens when the target is continuous? So when the target is continuous, what happens is that we are not talking of a classification tree, but we are rather talking of a regression tree. Right? So here, the target variable in a regression tree, the target variable is numerical. Okay. One task is that for a numerical variable, how do you measure homogeneity or heterogeneity? I can guarantee that everyone knows the answer, but yeah, just maybe apply your mind. For a numeric variable, how do you measure the homogeneity or the heterogeneity? Gaurav has given me the correct answer. Kaushani also has given me the correct answer. Samrat, the answer is again convoluted, right? Because answer is not correct. For numeric variables, how do you find out whether the data is homogeneous or not? Right? How do you find out data will be homogeneous or not for numeric variables? OLS, no, Samrat, not the answer. Many people have given the correct answer. I'm repeating the question. For numeric variables, how can you measure homogeneity or probably heterogeneity? Both. How can you measure? How may you measure the homogeneity or heterogeneity in numeric variables? Samit has given the correct answer, right? Okay. That's it. Everyone knows the answer. See, when we find out the central tendency, right? Central tendency is okay. How closely the data points are clustered around the center part, right? When we find out the variance or the standard deviation, right? That measures that how much the overall data is scattered around the central value. If your data is homogeneous, let's say all the data points, they are the same, the standard deviation will be 0, which means completely homogeneous data, right? If your standard deviation is more high and high, which means the data is much more scattered. A lot of deviation in the data, isn't it? So if you're having a lower variance, it's probably your data is more homogeneous. If you're having a high variance or a high standard deviation, right, then probably the inconsistency in the numeric data is high, right? Okay, so let me stop here, and now probably let me questions from your side, right? Questions, some of the problems that you're probably solving in your organizations, right? How can you apply these models? Yeah, we can probably discuss it. Please raise your hand. I'll probably unmute you. We can go into the discussion, and then probably we can call it a day. Yeah, questions. In the meantime, what I'll do is for the hands-on part, I'll share the files with you for the hands-on part. Download the files. Okay. In the meanwhile, as I said, that yeah, questions that you're having. Questions. Let me just give you the link. Questions. People seems very tired, so either they have understood everything, or probably the other way around. Please download the data set and the Python file from the link which I have provided. We'll be using that tomorrow to be hands-on. Kavita is asking, will we have calculations in the exam? Yeah, Kavita, I might ask small calculations. Not really big ones, but small calculations, so we can have, right, a small short questions kind of thing. Nothing like we have created, I mean, not elaborate like that, but yeah, small calculations I'll probably be giving. Right? Okay. Yeah, please download the data set and the Python file from there. Tomorrow, when we are going to do the hands-on, please keep this handy, that every one of us are on the same page, right? It's a very elaborate solution which is given there with a lot of very good explanation, right? So yeah, can just that. Yeah, questions before we move ahead. We still have some time, right? I can't finish before time, so yeah. Some questions if you're having, please ask. Please ask. Right? This should not be parked till the very end, where your only question becomes that what will come in the IA or in the midterm exams, right? Yeah, questions. Yeah, Samrat, please ask the question. Yeah, why not? Let me.
Yeah. So, so actually, why am I asking this is maybe a little bit slightly out of context for here, but nonetheless, so we are trying to implement the best. We are trying to implement a supervised to adaptive modeling way, right? So we have a classification problem wherein we are trying whether we can have a adaptive model to beat the performance of a supervised model. We are just checking. We are not claiming anything. So
I did not get your question, Samrat. So you are saying that you are trying to build a. So what do you mean by an adaptive model? What do you mean by that?
So we are basically using reinforcement learning or an agent-based modeling.
Okay, RL you are trying to build.
Yeah.
Okay, fine, fair enough.
So the point is, it's a binary classification, and it depends. It's about you can say a churn analysis. So based on the activities of the customers on the account over a period of time, we are to determine whether the customer will churn in next 7. What is the probability of churn in next 1 month or next 2 months, like that?
Sure.
Okay, so why we have used RL is because there is a lot of within a short time the activities are changing a lot, and hence maybe we thought to give that approach a try. So in order to do so, what we are doing, we are trying to implement various functions, right? So it's like suppose we take care of we calculate the sum of the last 8 weeks, last 10 weeks things, aggregate them, and put a feature and calculate a probability using sigmoid function, or
Okay.
that is to replicate a more or less logistic regression. So in that way, how we can actually replicate a decision tree type of function. Like
But again, what I understand is that the problem that you're talking about, that is more of a time series kind of problem, because
yes.
again the behavior, it changes with respect to the time, right?
Yes.
Yeah. So in that particular case, again, rather than using things like a decision tree or the others, why don't you try out something like the classical time series model, or probably some things which are like the newer ones, like those LSTM models which are there, long short-term memory kind of models, where it takes the longer kind of behavior also, as well as if something has changed the short run, that also it takes right. I believe that for the kind of problem that you're talking about, LSTM has very good this thing, results. Try out LSTM models in that, right? And let me know the next week that did you get some better these things or not, better results or not.
Sure, but we are supposed to do it in a RL way, like LSTM. They are saying like, why don't you try RL?
No, but again, RL is a different domain altogether, right? So when we are talking of RL, so RL, so you have this incentives as well as the penalty which is there.
Yeah,
reward and penalty, and again, depending on the class of the problem and how it's behaving, you basically adaptively you create the reward as well as the penalty, right?
Yeah.
So again, that's a very different class of problem, or different kind of approach compared to what you are doing, right? I can tell you that it will be interesting if you probably use LSTM kind of models out there, because at least for the class of problems which you are seeing, where pattern it changes very fast, and the recent patterns will probably have a more bearing on the data compared to the older patterns. Your LSTM kind of models will give very good results. Otherwise, see, even in your classic time series model, classic time series model also, you have this exponential smoothing kind of models.
Yeah.
So exponential smoothing model, what happens is that the newer data points or the newer performances are being given more weightages compared to the previous ones, right?
Yes.
So try out a mix and match of all this. Finally, at the end of the day, you should be able to build a good model.
Yeah.
Right? And whether it is coming from a supervised model or a RL model, right? It should not bother you much. If you build a good model, and then if the requirement is that the model should be explainable as well, as long as you're able to satisfy this criteria, be good.
Okay. Yeah, great.
Right? Okay, fine. Any other questions that you're having? Any other questions that people are having? Any other questions that people are having? Right. Once again, a small piece of advice to everyone. One part is, again, as I said, that depending on the batch composition and your objective, right, there might be different motivations for you. Take up something like a data science machine learning kind of a specialization in your MBX. Now, some of you might be working as a business analyst. Some of you might be working as team leads. Some of you probably might only be probably are already working as data scientists, which I understand, right? So again, depending on whatever it's very important that one understand what the business is talking about, right? So understanding of the business context is very important. Two, that at least whenever you are conversing with let's say your teammates, or let's say with your customer, if question comes in terms of okay, why this model is good, how can you ensure that? That is where the explainability part, which we are discussing, the mathematical part, that comes into play. So yeah, maybe in your day-to-day life, you'll not have to work with this mathematics part. Most of the cases, the software will do it for you. Again, if you don't understand the interpretation of these numbers which you're getting, the maths that you're getting, everything else might fall apart, because if you're unable to explain, then probably you are as good as a blind model, right? So yeah, that's it from my end today. So yeah, keep learning, keep asking. So yeah, we'll meet again tomorrow morning, right? Tomorrow morning we'll do some hands-on, we'll complete the regression tree, and we'll go to the model selection part, right? Go to the model selection part. This particular part of the machine learning, it's a bit of theoretical. It's a bit of theoretical in the sense that this different models are there, why these models are being applied. In fact, tomorrow when we talk about the model selection part, so model selection part, a lot part will come in as the understanding that okay, what kind of a different model selection techniques are you going to use? For the implementation part, those one or two lines, right? It's mainly the strategy as to why some particular methods are being used and where to use them over the others, right? So yeah, for that, a bit of the theory will be required. I understand that for some of you, theory is not that interesting, but yeah, I think we should try to cover this. So again, that's all from my end, right? But yeah, what we are going to do is, I think I'm coming between you and your dinner. So yeah, enjoy yourself. We'll meet again tomorrow. By the way, Samrat is having a question. Are we going to cover deep learning? So deep learning is there in term 3, but again, from whatever I know, is that, I mean, it's covered in a very basic manner, right? So if you're being asked by clients to explain DL models, right now, that's not going to happen from your MBX. Might have to enroll for some other small deep learning modules. MBX, at least whatever syllabus I have seen, to the best of my knowledge, it doesn't cover DL in details. Fine. Okay. Thank you, everyone. Good night. And again, meet again tomorrow morning, 10:30 sharp. Good night, everyone. Take care.